how much of the, I didn't notice it. I'm not sure how much of the video I've missed. I mean, how much of the lecture. Anyway, we'll continue on here. So let's do the next step. The next step is, one of these we'll just write as is. And so the oxidizing agent, we usually just write as is because of the table. Nitrate plus 4H plus 3 electrons yields NO gas plus 2H2O. Still up. Okay, this is our oxidizing agent. What must this be here? This is our reducing agent, the conjugate reducing agent. Okay, we do this to figure out what the driving force is, and these are called half reactions. At the half reaction stage, where you see the electrons, that's the easiest place to assign these because of the conjugate relationship. All right, now the other reaction we have to write in the reverse direction because we don't have gold with tetrachloroborate 3-ion, we have gold solid. And so it's going to be gold solid plus 4 chlorides yields this. We could just read it off there. The AuCl4 minus plus 3 electrons here. And so when we do this, this is going to be the reducing agent, and therefore this must be the conjugate oxidizing agent. Here. See that here. It's on the other page. Now what we do is we add these up so that the electrons balance. We can't have electrons left alone in the reaction because electrons as a reactant or electrons as a product you can't buy. Can you buy a bottle of electrons from the store? No. But you might think, oh, maybe I can package a bottle of electrons. Can you package a bottle of electrons? No. And so we can't have free electrons left. They have to cancel out. And so we're lucky here because it matches. So it looks good. So we're going to get nitrate plus 4H plus. The 3 electrons cancel. Then we're going to get gold solid plus 4 chlorides. Those are all the reactants, and all the products are going to be NO gas plus 2H2O liquid plus AuCl4 minus. All right, can we cancel anything out further? No, we can't simplify it any further. And so the last step is to look for driving force. So the driving force is, this is our OA on the left. Our OA on the right is this. And so let's try to figure out what's the stronger OA. To figure out what the stronger OA is, oxidizer, we start off at fluorine and work our way down. So starting off at fluorine, we work our way down and we get to which one first? Okay, nothing here yet. Here, tetrachloroborate. Tetrachloroborate versus nitrate and H+. So tetrachloroborate is it. so because of the conjugate relationship, if the oxidizers are like this is weaker, this is stronger. If the oxidizers are like this, then the reducers have to follow the same pattern, unless I screwed up the oxidizers. So this must be a weaker reducer, this must be a stronger reducer. And so let's just take a look. So we're comparing NO and H2O. Which one would be closer to fluorine? So looking at here's NO and H2O. Here's gold and chloride. And so it looks like NO and H2O are closer to lithium, so that's correct. And what we say is this. We say that we're going from weaker to stronger. That is, weaker is, no, did I get that right? Is that right? Yeah, that's right. Weaker is more stable or less stable? Weaker. Like a stronger acid, what would you rather spill? Or a stronger acid or a weaker acid? Weaker because it's more stable. And so what we're doing is we're going from more stable to less stable. Going from more stable to less stable, does that look like a good driving force? No. Right? And so this is not a driving force, so therefore we'd say no reaction. We say no reaction because there's no driving force. And so yet again, it didn't react. It didn't react, right? But, you know, it's a well-known fact that aqua regia, does aqua regia really work? You know, we predicted it doesn't work here, right? Aqua regia doesn't work here.
Hey, spell nerds. This.
A lot of audio works in here.
This reaction produces hot. Greetings, spell nerds. In this video, we're going to dissolve a gold chlorine acid. Here is the coin. It's a 1/20th troy ounce Canadian nickel. Now we add 10 milliliters of concentrated 12 molar hydrochloric acid. By itself, the acid does not react with gold, so we add another 1 milliliter of concentrated 50 molar nitric acid. The mixture is gently heated to speed up the reaction. Eventually, the mixture will turn yellow and bubble as the gold starts dissolving. We showed in a previous video that gold will not dissolve with either hydrochloric acid or nitric acid alone. What's happening here is that the nitric acid is first oxidizing the surface of the gold. Then the chloride ions and hydrochloric acid react with the gold ions to form a complex ion that dissolves away in the solution. The gas, push off, forget. Eventually the mixture will turn yellow and bubble as the gold starts dissolving. We showed in a previous video that gold will not dissolve with either hydrochloric acid or nitric acid alone. What's happening?
All right. What's happening is this is actually a combination of reactions. This is a combination of a redox reaction. Here, the nitric acid is an oxidizing acid. It's a powerful oxidizer, much more powerful than HCl, which is considered mineral acid. So the nitric acid attacks the gold. Gold forms gold 3, but is gold 3 stable? No. And so what we could do to help stabilize it is we could do this.
Here is that the nitric acid is first oxidizing the surface of the gold. Then the chloride ions and hydrochloric acid.
Okay, the second reaction, this is an example of what we call a Lewis acid-base reaction. There's a gold 3 we call a Lewis acid. You know, it's a positive species, typically Lewis acid, negative species, Lewis base. Chloride acts as a Lewis base to form the tetrachloroaurate 3 ion here, and that helps stabilize it. But does it help stabilize it enough? Because what we did was we predicted no reaction. We predicted no reaction, but when you look at that video, there's plenty of reaction there. That was a 1 troy ounce gold coin, but it's no longer going to be 1 troy ounce. Fortunately, why would you do that? Why would you want to do that? Well, fortunately, matter is neither created nor destroyed in chemical reactions, so they can recover all that gold. It's not that hard to get the gold back. It won't be nice. It won't be a perfect, shiny new coin like that, though. Chunks of gold. But why did the reaction occur here, and yet when we did this, hey, we predicted no reaction? Can you tell me? Uh-huh.
They use concentrated
Yeah,
acid.
yeah, they used concentrated acid. What did we use in our prediction? What did we use in our prediction? What concentration did we use in our prediction?
Normal concentration.
What is normal concentration? We don't call it normal concentration either. But it is normal concentration. What is normal? It's not really normal because there's no such thing, really. It depends on what type of reaction you do. 1 molar. What's that called? It's one standard conditions. Because we assume standard conditions. Something like this. The thing is, like, okay, I don't know. Maybe I only talked about it yesterday, but you don't want to just listen. When you listen to somebody, you don't remember those things. Blah blah blah. It's just when you put it in your own words, that's when you remember it. And so you go back through what I say, and then you rethink everything I say into your own words, and you'll remember it. Otherwise, think about the delay it takes you there. On standardized tests, there's no time for delay. If you're taking a standardized test, it's boom, boom, boom. They want to see, is this the reason why standardized tests, they aren't meant to be finished. They have way too many questions. The reason they do that, I think, is to see what level you're at. Have you deeply ingrained the basics in your memory, so that way you can do more advanced problems? One of the common complaints in Chem is the test question's nothing like the homework. The test question's everything like the homework. There's a running joke about hearing this question a lot because it's just that people just didn't understand the material well enough to apply it. It's just like, that ion wasn't on your list. Well, you didn't understand the material well enough to apply it. And so this is why I think standardized questions are crazy like this. I mean, they have, well, anyway. So, when the concentrations change, these 15 molar, when concentrations change, obviously it's going to alter the way it reacts, right? And we have to adjust things. But, do we want to have to do this for all the... No, we don't want to. We just want to keep things under standard thermodynamic conditions and make our predictions. And our prediction would have been if we use 1 molar and 1 molar, actually, if we made the solution to 1 molar, if we made the solution to 1 molar in both acids, would this reaction have gone? No. It's just by increasing the concentration, we can force the reaction to occur. What we think of in terms of this is, and this is one of the things I was thinking for chapter 13 because I wanted to talk more. Chapter 13, the application of that is this. In Chem 1A, this is Chem 1A type level. At the Chem 1A level, what we think in terms of are qualitative. These are very qualitative driving forces here. In Chem 1B, we step it up. In Chapter 13, which is Thermodynamics Part 2, what we want to do is we want to put a number on the driving force. And so what is the driving force here? Well, the driving force is, it's not pushing it, it's actually the driving force is in the reverse. You know, the reverse reaction is more favorable because if I mix tetrachloroorate and NO in water, the reverse reaction is more likely to take place. And so what we have here is something called an equilibrium here. You know, what we're doing is, it's a competition between the reactants versus the products. Which one's more reactive? That's the direction. It's going to go from the more reactive to the less reactive. Or in terms of activity series, it's going to go from the more active to the less active. And so, you know, what we're going to do in chapter 13 is we're going to put a number on this. And then in chapter 13 we go, do you want to do every single reaction under standard conditions? You know, do you? No, we don't want to do every single reaction under standard conditions. We'd like to go non-standard conditions as well. We'd like to go non-standard conditions and predict the driving force. So for example, if we want 15 molar and 50 molar, would we have seen a driving force here, and how big of a driving force quantitatively would we have gotten? You know? And so that's a powerful tool. The thermodynamics is an extremely powerful tool in predicting driving force for chemical reactions. But the first part of this is to first understand this qualitatively. To understand this qualitatively, you know, there are certain things that you can think of. For example, here, if we want to try to help the forward reaction, there are certain things we could do. We could try to increase the concentrations. We could try to maybe change the temperature. You know, if this is an exothermic reaction, we could try to, what would help an exothermic reaction go? If this were exothermic in this way, we could try to lower the temperature. You know, freezing water. When you have water, when water freezes, it's exothermic. You got to take heat away from water, energy away from water, to freeze it. And so we take kinetic energy away from water, we freeze it, then. So that helps. So we could try to change the temperature. You know, if it's endothermic, we should increase the temperature. You know, melting ice is endothermic. If you want to melt ice, you try to increase the temperature, add heat to it, right? Uh-huh.
So not all chemical reactions occur faster than temperatures?
All chemical reactions occur faster at higher temperature, but it's a competition between the forward reaction and the reverse reaction. And so if you're trying to form products and you increase the temperature, both sides get faster. But which side is more favored, you know? That helps. And so the thermodynamics part of it is, you know, things will collide, occur faster, but which side is favored depends on if it's exothermic or endothermic. You know, it depends on which side of the hill it's on. All right, for this exercise, we're just doing this qualitatively. We're doing this qualitatively so you can get a better understanding of the reactivity of chemicals. Because reactivity changes depending on things like temperature, concentration, all these other things. So what we need to do is we need to keep everything fixed so we can understand, you know, which one's more reactive, nitric acid or some other acid, chloric acid, you know. Which one's more reactive, you know, gold or silver. You know, we try to keep things under these. And then once we get a better feel, we want a better feel, then we know we can tweak the conditions to try to prevent reaction. Sometimes we try to prevent reaction, or sometimes we try to enhance reaction. So we could try to tweak the conditions to enhance the reaction. That's thermodynamics in detail, you know, and that's chapter 13 we're going to get into. But for right now, we're not there yet, and so we just say this is no reaction. Aqua Regia works fine under the right conditions. Sometimes we don't do the thermal. Sometimes you just mix it and see what happens. And that's something called skeleton redox. And skeleton redox Well, we're going to continue this with some examples later, but I'll write some of these reactions that we're going to do as examples. Do some metathesis, some redox. So the redox we'll try out. Copper with nitric acid. These are potential diagrams. Potential diagrams here are more advanced. That is something like manganese. You know, manganese has a whole series of oxidation states it goes through. Here's manganese 0. If you look in the magenta up there, the letter. Manganese 2 plus, manganese 3 plus. Here's manganese in the +4 oxidation state. Here's manganese in the +6, and here's manganese in the +7 oxidation state. So it can undergo this series here. It's like carbon. You know, do you oxidize manganese completely, or do you oxidize it partially? If you oxidize manganese completely, it's going to oxidize all the way to permanganate. Can you go beyond permanganate? No, because you hit the max. I mean, +7 is it's lost all its valence electrons and the d electrons as well. And so here, but you know, you need a pretty powerful oxidizer to do this, to go all the way to permanganate. If you just have a weak oxidizer, it might just take it to manganese 2 plus, or a little stronger to manganese 3 plus. So it depends on the strength of the oxidizer. You can partially oxidize it, or you can completely oxidize it, depending on what you mix it with. And so in our bodies, like say, if you have something like ethanol, you know, ethanol is not oxidized straight to CO2 in our bodies. You know, ethanol goes through a series of oxidations. So you start at ethanol, and then you go to, you know, maybe acetaldehyde or acetic acid, etc. And so it goes through that same type of situation. Potential diagrams we do not work with. Chem 1B, that's beyond the scope of Chem 1B. Skeleton redox, this is just chapter 5. At the end of chapter 5, sometimes, you know, sometimes it's easier, rather than, you know, trying to predict, there could be multiple products that form, depends on the strength. Do you see that? You know, do you oxidize it all the way, or do you oxidize it partially? Tell me, under what conditions, let's say I want to generate carbon monoxide for some experiment. Under what conditions will I get carbon monoxide? That is, tell me what adjustments I should make so that I'd like to get 100% carbon monoxide. You think that's easy to do? No. We can play around with conditions and see, but we're probably going to get a mix of products. We can try to see how we can maximize the carbon monoxide that's being produced here. Carbon monoxide is highly toxic. Lots of people die from carbon monoxide poisoning every year. But sometimes it's hard. You know, sometimes what's easier is not to try a theoretical approach. Sometimes what's easier is just to try a descriptive approach. A descriptive approach is just, I'm going to play with this, adjustments, and then just measure the carbon monoxide coming off here. And then, once I see the max, then I say, okay, that's about the most carbon monoxide I'm going to get from this. You know, that's kind of a descriptive approach, right? You just play with it and see. Well, that's what skeleton redox is. For skeleton redox, we do not predict the products of the reaction. The major products are given. The reason the major products are given is because they just mixed it and see what happens. So here we're using ethanol to reduce permanganate. And so permanganate is going to be our oxidizer. Ethanol is electron rich. I told you about the way I do oxidation states is I like to do it based on structure. We have three ways of counting electrons in a structure. One is the octet. 2 is the formal charge. 3 is the oxidation state, or it doesn't have to be in that order. Okay. What's the difference? when we count an octet, how do we count it? How would you tell? What's the difference between, there are 3 ways of counting the electrons. For example, this carbon has an octet, right? That's good. The hydrogens want a duet, but the carbon wants an octet. How would you describe counting? How can this carbon have an octet of electron? Octet of electrons is 8. How does it have an octet of electrons?
It already has 4 valence electrons.
It's 4 valence electrons.
It wants 4 more.
It wants 4 more. So. Does it have an octet? Does it have an octet? Yeah, it has an octet because when we count an octet, we count all the electrons surrounding it. So, and then that's 2, 4, 6, 8. That's 8 electrons, right? What's the formal charge on carbon? Zero. Okay, what does formal charge mean? Its formal charge is 0. Okay. Formal charge is what? Give me a 1-sentence definition or half-sentence, a phrase definition of what formal charge is. Formal charge is, when I ask people what the formal charge is, they just tell me the equation. Oh, this is the equation to calculate the formal charge, which is meaningless, because I want to know what it means. The leftover electrons? Leftover electrons from what? I mean, okay. That's kind of the equation. It's the leftover electrons after you do the calculation for the equation. That's it. But, and it is, sometimes there are leftover electrons, which gives you a negative formal charge. Sometimes they're missing electrons, which give you a positive formal charge. See, the thing, all you guys are pursuing science. The thing about science is, you have to start thinking in terms of, you have to shift the way you think. I told you, did I tell you when I transferred UCLA, I took thermodynamics? I had a rough time. It's because I wasn't thinking the right way. I wasn't thinking about the material the right way. I was thinking like, I can do that calculation. I know how to calculate formal charge, no problem. But if somebody asked me what formal charge was, I couldn't tell them. Just like you. You can't tell me what formal charge is, can you? Well, you aren't going to get very far that way. And so you have to start thinking, this is why I say when you get something like formal charge, you don't read what the book says. Sometimes, maybe the first step is to memorize the book's glossary definition of formal charge. But eventually you want to take it a step beyond that and you want to put it in your own words. In my own words, this is what formal charge means to me. And then you're thinking the right way. And you'll be much more successful, I think, that way. But I'll tell you, formal charge and oxidation state, when I think of formal charge and oxidation state, they're tied. They're two opposite extremes. Formal charge assumes that the electrons in the structure, actually, this is it. Formal charge is counting the number of electrons, assuming that the bonds are 100% covalent. If we assume all the bonds are 100% covalent, then this is how we count the electrons. We count the electrons like this. If this is 100% covalent, it's 50-50 sharing. So 1 electron goes to hydrogen, 1 electron goes to carbon. This is already 100% covalent because carbon versus carbon should be 100% covalent. What do I mean by 100% covalent? Each electron shared equally. And so if we do that, then half the electrons belong to the other species, the other half belong to carbon. So how many electrons belong to carbon? 1, 2, 3, 4. 4 electrons belong to carbon. How many electrons is carbon supposed to have? How many valence electrons is carbon supposed to have? 4. So it has 4 electrons. It's supposed to have 4 electrons. It broke even. So the formal charge is we circle. Formal charge is 0 on carbon. Now oxidation state, what's the oxidation state on carbon? If you look at this, tell me what the oxidation state is calculated based on the formula of ethanol.
I'll take a shot in the dark and say -2 is what I count.
-2. Let's, anybody else? -2?
Is it wrong?
No, I don't know. Let's check it. +1 plus 5 is +6. -2. Okay, +6 minus 2 is +4. And that means we have to have a -4. 2 carbons and a -4 means each one is -2. You're right. But you know what we call that? We call that the average oxidation state. The average oxidation, this is just the average. You know, if you said, okay, what's the average? The average is this number, but you know that average is based on what? That average is based on the individual measurements, and you know what's the extreme values of that. You know, if I told you the average bond energy of an oxygen-hydrogen bond is 436 kilojoules per mole, that's the average. Well, what's the low end of that average? What's the high end of that average? Do you have any idea? No idea. You have no idea what the spread is, right? What the individual measurements is. And so when we have the average, we kind of lose that unless we... that's why scientists never report the average. When scientists report an average, they'll have an average plus or minus. They'll have an average plus or minus something called lambda 95. Lambda 95 is a 95% confidence limit that says within this average, there'll be a range of values where 95% of the measurements will have fallen under. And that gives you a better idea of the spread. We're going to do, I have I do lambda 95 in Chem 1A. No. But anyway, what is the oxidation state on this carbon? -2? No. Sometimes yes, but not in this case. The oxidation state on this carbon is not -2. Do you know what the oxidation state on this carbon is? -3. The oxidation state on this carbon is -3. How did I figure that out? I could do this in my head because it's not that hard. You could do it in your head too. It's not the number of hydrogens it's attached to necessarily. You know, that's probably a good pattern, but it doesn't work all the time. Because using that pattern, what's the oxidation state on this carbon? If this is -3 because we have 3 hydrogens, this would be -2 because we have 2 hydrogens. The average would be -2.5. Is the average -2.5? No, so it didn't work. We have to find something else. Maybe you could reverse engineer it. If I told you the oxidation state is -3 here, how did I get that number? Actually, I don't want you to reverse engineer. All right, if formal charge is based on assuming the bonding is 100% covalent, then oxidation state is based on the bonding being Paul, you remember? No. How about Kelly? You remember? Yeah, that's correct. Ionic. what we do is we assume that the bonding is 100% ionic. If it's 100% ionic, what does that mean? Is it shared? No, it means, this is in my words, but do you have your words for it, Kelly? What does 100% ionic mean? I called it, winner take all. That's what I call it. Winner take all. Winner take all means if there's a tug of war, hydrogen versus carbon, who's going to be the winner? And why? Carbon's going to be the winner. Why? That's more electronegative. So the carbon versus carbon, which one's the winner? Unfortunately, carbon versus carbon, we can't have winner take all because it's got to be a tie. And so here, sorry, it's not always winner take all. Sometimes there's a tie if they're totally even. Carbon versus carbon, you can't win. Now let's count the electrons. 1, 2, 3, 4, 5, 6, 7. Now it has 7 electrons. It has 7 electrons. What does that mean? Well, it needs one more for the octet, but if it has 7 electrons, what does it mean for charge? It means it has 3 more electrons than its valence. So the oxidation state is going to be -3. Yeah. Let's do the same thing. Winner take all here. Hydrogen loses, carbon loses against oxygen. It's 1, 2, 3, 4, 5. It has 5 electrons, which gives it a -1. -1 and -3, the average is -2. Because carbon normally has 4 electrons, it has an extra. It has an extra electron. Each electron is -1.
Okay.
So, oxygen, you can take all of them. It's going to end up with 8. It's -2. Hydrogen ends up with nothing. It's +1. Those are oxidation states. So we could see, this left carbon is much more electron rich, but both of them would be considered electron rich. This one is much more electron rich. And so eventually you're going to have to do this when you get into larger molecules. But you look for, the active, what's portions of the molecule or the reactive portions. Well, anyway, under these conditions, because we could change the conditions, this is a partial reduction of permanganate. If we had full reduction, it'd go all the way to manganese metal. But this is partial reduction of permanganate. And you have to adjust the conditions because, under certain conditions, we don't know which one is going to form. There's a whole series, right? It's like this. We adjust this until we get more carbon monoxide or more soot or whatever. That's the conditions, and then this is it. And so in skeleton redox, we have this. Do you guys remember the steps? Split it into skeleton half reactions and balance. Balance all elements other than hydrogen and oxygen. Balance the oxygens by adding water. Balance the hydrogens by adding H+. Balance the charge by adding electrons. Combine the half reactions, etc. So we have some examples of these to work on. Let me just go through the brief run through and then we'll do some practice examples here. But acid-base reactions are the last type of reaction. We have 3 different ones: Arrhenius, Bronsted, and Lewis. Bronsted is the one we're going to focus most of our attention on. The difference between these is the definition. We only need one. We could eliminate Arrhenius, we could eliminate Bronsted, and Lewis acid bases encompasses all acid-base reactions. But the reason we keep all these is because sometimes it's easier to look at a subset of acid-base reactions. Lewis is the complete definition, but if we look at a subset of acids and bases called Bronsted-Lowry acids and bases, our life is going to be much easier. Arrhenius is not very useful. So let's go to Bronsted. A Bronsted acid is a proton donor, Bronsted base is a proton acceptor. And so when we do the Bronsted-Lowry acid-base method, we don't do complete reaction. What we do is we inventory it like redox, and then we determine the strongest acid and the strongest base, just like redox, except we use a different chart. We use the acid-base chart. And then we transfer a single proton. In redox, we can transfer not a single electron. Sometimes we transfer a single electron, 2 electrons, 3 electrons, 5 electrons. In acid-base, we're always transferring a single proton. This is why I did all caps there. Determine the driving force, if any. Repeat 1 through 4 to determine if further reaction occurred. So these are all in the PowerPoints here. So something like this, phosphoric acid and sodium hydroxide, we do have 2 approaches for that. We could do that, phosphoric acid and sodium hydroxide could be a metathesis reaction. What's the formula for phosphoric acid? H3PO4. The formula for sodium hydroxide? Anyway. And so this is an AB plus CD type pattern. What forms from this? Sodium phosphate. Actually, what's the formula for sodium phosphate? Na3PO4. And water. Water is liquid. Sodium phosphate is AQ. Now, this is what you're going to have to do. The reaction you were working on Tuesday, you're going to have to tell me all the driving forces present. Is there any driving force present here before? I don't want to balance it if there's no reaction. And so before I balance it, I want to determine if there's a reaction. Is there a driving force here? Yeah, this is metathesis, AB plus CD. Not solubility, it's going to be what are the driving forces for metathesis? I'm sorry? Yeah. Well, not those. 3.
Strong acid forming for weaker acid.
It doesn't have to be strong, it just has to be stronger. So stronger, it could be a weak acid just going to an even weaker acid. A stronger acid to weaker acid, that would be in this case. This is a weak acid, but it's stronger than this. This would be the acid, the proton donor. So it would be stronger acid to weaker acid. This is what we call the driving force. Precipitation is the other one I was looking for, and gas formation is the last one I was looking for. There's no precipitation, there's no gas formation here. We're just going from stronger acid to weaker acid. So we'll go ahead and balance this. This is going to be 3 sodium hydroxides. This is going to be 3 waters, and it's balanced. Then we do, this is what we call the complete, and then we do the ionic or total ionic equation, and then we do the net ionic equation. Do we dissociate phosphoric acid in the ionic equation? No, it's a weak acid, so do we dissociate weak acids? Do you dissociate weak acids? No. No. And so we leave it alone. Let me briefly mention something that people do. If I have a dichroic acid, like H2SO4, do both protons break off the acid at the same time? Like there's, a pull cord and both protons break off simultaneously. Do you think that happens? No. When a base comes, a base is going to try to pluck the proton off. Let's say water. Water is the base. Water is very interesting because water is both an acid and a base. It's amphoteric. That's what we call amphoteric. Water is also both an oxidizer and a reducer. So water is pretty interesting as far as chemistry goes. Anyway, here, if a base comes along like water, it plucks a proton. Do you think the two waters coordinate the attack? Two waters are going to coordinate the attack on the sulfuric acid. So 3, 2, 1, pluck both protons off at the same time. Do you think that happens? Do the waters communicate with each other? No, what do you think happens? What happens is one proton gets plucked off. If one proton gets plucked off, then we get this, right? And we know that this proton's easy to pluck off because this is a strong acid. And so the first proton gets plucked off easily. How about the second proton? Now, okay, the first water comes in and say, oh man, that was easy. I was able to pluck that proton off. Because you know what H plus AQ means? H plus AQ means hydronium. But, H plus does not exist in water. But it's a pain to write hydronium, so I use H plus. It's easier. The charts use H plus. It's easier. But H plus doesn't exist. Why? Because H plus consists of what? What is an H plus made out of? It's just a proton. How big is a proton? How big are atoms? Let's say, how big is a hydrogen atom? You know about how big a hydrogen atom is? 1 angstrom. And how big is a proton? 1 angstrom is about how many picometers? One angstrom is about 100 picometers. And so I don't know what it was. I think in the Chem 4, the Chem 1A book, they're saying angstrom is dated. Angstrom is 10 to the minus 10 meters, but angstrom's still useful because atoms are about that size. In fact, angstroms were developed for atoms, But anyway, so it's about 100. How big is a proton? A lot smaller than that. A proton is like tiny, right? And if you get rid of this and you're just left with this tiny proton, what's the charge on that tiny proton? +1. And what did we say about this? What the proton has extremely high charge density. It's way too reactive. It's not going to exist. So it's going to attack a water and form hydronium easily. But, it's up to you. I saw that some people were writing hydronium, some people were writing H+. My preference in Chem 1A is to write H+, rather than hydronium. And we know that H+ doesn't exist because of its extreme charge density. It's not going to happen. But let's continue on with this. HSO4-. The first water comes in and says, that was easy. Easy to pluck off that proton. Now I have H plus AQ, the water is getting that proton, right? Now the second water comes in. Do you think the second water is going to have as easy of a time plucking off this proton? No, the second water got the short end, right? The first water had an easy time because this is what we call a strong acid. The second water is going to have a huge fight to pull off that proton. In fact, do you think that second water is going to be very successful in pulling off that proton? No. The second water is going to have an extremely hard time plucking off this proton because this is not a strong acid. This is a weak acid. Weak acids have stronger bonds. Weak acids are more stable. Weak acids are less reactive. Right? And so this. Do you think this one's going to lose that proton? No. This one's going to fight and it's going to hold on, and the second water is going to have such a hard time pulling it off, it's not going to be very successful. So we stop here. When we ionize H2SO4, it does not ionize into 2H plus and a sulfate. Because that means both protons were stripped off easily. No, that doesn't happen. So when I go to the ionic equation, it's H3PO4. Oops. When I go to the ionic equation, in the complete equation, we show this. In the ionic equation, we would show H plus and HSO4 minus. We wouldn't show two H pluses and SO4, 2 minus. That's getting back to the earlier problem I talked about. What we were doing. This is chapter 16 stuff. Did you guys cover the end of chapter 16? What makes a good Bronsted acid, Bronsted base? This is something else you want to review. The end of chapter 16, which talks about structure in acid-base reactivity. For Lewis acid-base reactions, we have a little different definition, and this is the broadest. A Lewis acid encompasses all acids found in nature. And so all Bronsted acids are also Lewis acids, but not all Lewis acids are Bronsted acids. And so if you don't want to miss any acid-base reactions, then you have to understand Lewis as well, because Bronsted misses the whole class. Like, for example, this. Ammonia is a base. Well, it's a Bronsted base and a Lewis base, but BF3 turns out to be a good, strong Lewis acid. And the difference is in the definition. The definition is a Lewis base is an electron pair donor. A Lewis acid is an electron pair acceptor. Okay, so if we have an electron pair being donated and an electron pair being accepted, then we form a covalent bond. This is called a coordinate covalent bond, or dative bond, or complex. And that is, it's called a coordinate covalent bond because both electrons in the bond come from the base parent. When we identify Lewis acids, it's a little different than identifying Bronsted acids. Bronsted acids are easy because Bronsted acids begin with an H. When we look for Lewis acids, we have to analyze the structure. And one molecule can have both. It could have Lewis acid sites and Lewis base sites in the same molecule. And so the same molecule can act both as a Lewis acid and, well, we know one that can do that already, water. But there are lots of other molecules that can act both. And we look, which atom is or which site is the Lewis acid, which site is the Lewis base. The strength of Bronsted acids is easy. We have a Bronsted acid table. The strength of Lewis bases is much more tricky because there's so many different types of reactions. And so what we use for ranking the strengths depends on what acid and what base are being mixed. And so we use something called HSAB. HSAB is hard, soft, acid-base theory to better understand it, or we use quantum mechanics. HSAB is based on quantum mechanics, but it's just simplified so we can just do it by pencil and paper rather than have to do it by computer. And so this hard, soft, acid-base theory is useful. But what you understand here is this, the take-home message, because HSAB is beyond the scope of this class, so the take-home message here is that ranking Lewis acids and ranking Lewis bases is much more complicated than ranking Bronsted. Ranking Bronsted is so easy. I don't know. Should have opened this in Chrome. But here's the Lewis. This is not Lewis. Here's the Bronsted acid base table there. It's easy. Do you know how to rotate this?
I think up on top, see that little curve button? No, not there. That button that you click will say original.
All right. Actually, no, I want to do that. I want to. They have some other PDF. Adobe. Well, I don't want to waste much more time. All right, so ranking Lewis acids and bases are much more difficult, but ranking Bronsted acids and bases are much easier, but it's not always so easy. What's the Adobe PDF viewer? Adobe. I've been using Nitro as my PDF viewer, so I can't even remember what Adobe's PDF viewer is called. Somebody know? Acrobat, that's it.
It's installed now.
Yeah, okay. Well, I can't install anything on this computer, so I don't have privilege to do that, but Illustrator is installed. So okay, does somebody know how to rotate in Illustrator?
Control R. Control D and then.
All right. Well, they just re-imaged these computers, so they had Acrobat. That's just rotated easily in Acrobat.
Do you have a projector? Because I have a printer. If you have a projector, we could put it on it.
Oh, all right.
That would help.
Actually, I do have a projector. If you have a printer, that would be great. I mean, I just need to talk about one thing. So this is really easy because Bronsted acid, HClO4, is at the top of our list, right? And then we have the strong acids. These are all the strong acids here. And so HI would be weaker than HClO4. HI, and then HBr, HCl, etc. But there's one thing you got to know about this chart, and that is something called the leveling effect of strong acids. Have you heard of the leveling effect of strong acids? You guys remember the leveling effect, Kelly, Paul? No? Kelly, no? The leveling effect of the strong acids just means this. Water has such an easy time with any of these, it can pluck it off 100%. And so if water comes and plucks this proton off easily, then all these are the same strength, because these will be fully ionized. And so these guys are going to be 100% ionized in water, which means you just have hydronium, or H+, and the anion. And so they're all equal strength. Does HClO4 yield more H+ than HI? No, they yield the same amount of H+. In water, therefore, they're equal in strength. And so in water, all these are a tie. It's just when we get to here, for example, when we look at trichloroacetic acid here, or HSO4 minus, these are partially, there's going to be more of a fight. And so these, the stronger it is, the more ionized it is. The weaker it is, the less ionized it is. And so these will have different strengths. This is the leveling effect of strong acids. We also need to know the leveling effect of strong bases. All these bases essentially have the same strength in water as well, because all these bases, when you put them in water, they pluck hydrogen off water. They do something called hydrolysis. Bases hydrolyze water. And so methite comes in, plucks a hydrogen off water, forms methane and hydroxide. Hydride comes in, plucks hydrogen off water, forms hydrogen gas and hydroxide. All these produce hydroxide easily, and they all produce roughly the same amount except for oxide. Oxide will produce more, but all these others will produce one hydroxide. This one will be slightly more too. And so there's a leveling effect of strong bases. In fact, this is why. The strongest base that can exist in water is hydroxide. None of these bases are stable in water. The strongest acid that can exist in water is hydronium. This is it. That's the strongest acid that can exist in water. And so we have this chart that we'll be using, but there's one complication in using that chart, and that is the leveling effect. All right, so I just want to finish up this reaction stuff right now, and then we'll do some practice examples. But it turns out that Lewis acid-base reactions are a heck of a lot harder. So, well, not a heck of a lot. All of them are hard. It's just for Lewis acid-base reactions, we're going to do a lot more work. So, for example, if we do carbon dioxide as bubbled in water, CO2 in water. First, we look, is that a metathesis reaction? Are there ions? Can we do a favorable ion combination? No. Is this a redox? Well, it could be because water is an oxidizer and reducer. What do you think carbon dioxide is? Do you think carbon dioxide is an oxidizer and a reducer? No. In fact, I would think carbon dioxide is it's not on our chart. I already know carbon dioxide is not on our chart because I've read our chart. And so I can save a lot of time by not having to look at the chart. Carbon dioxide is not on our chart, but I know it should be a... Megan, you remember? What do you think? It should be a... Well, the first thing we do is we look at the oxidation state. Oxidation state on carbon is +4. This means it's only an oxidizer. So this is oxidizer, this is a reducer. But, these are weak. How do I know they're weak? Because this is factual data. CO2, is it a powerful oxidizer? No. If CO2 is a powerful oxidizer, why do they have CO2 fire extinguishers? CO2 fire extinguishers are meant to put out the fire, not fan the flames of it. And so this is weak, so I don't really worry about it. And so we try acid base. Do you see any Bronsted? There's no Bronsted acid base. Then we go to Lewis. And we're here at Lewis. We'll end up using that. And for Lewis, we got to draw out the Lewis structures. And we'll take a look at this. Well, I've been talking too long probably. Let's take a break for 15. We'll start at 11:20. Like that. We'll take a break for 15 minutes.